All right, so our goal here is to find the region whose area is equal to the given limit. So basically, this is crazy sigma notation that represents the area under a curve. And our goal is to find out the equation of the curve and what its boundaries are, like its domain, like from where to where. So there is a curve related to tangent, because I can see it right there, that looks like this. I'll just draw it like this. All right, so the curve looks like that. We have a bound, like a lower bound, like an A and a B, and we like an upper bound, and then we have to find the area. Well, actually not find the area. We have to find the equation of that curve that represents this. So this right here represents the area. So this right here is the area of the curve. Our goal is to find the area, the equation of the curve, and also to find that and to find that. Okay. And you want to start with like the most generic limit function that looks like this, almost the same as this, but you're going to write the limit as n goes to infinity, sigma I equals 1, n, you're going to go f of xi delta x. Okay, and f of xi is, you got some function. So this is the curve, basically, the equation, that's the equation of the curve, okay? And xi is a very smart input value, a smart input value. And I'll explain that in a second. And delta x is the width, or delta x is, I'll explain that right now actually. So the way this, I'm going to rewrite this whole thing. Actually, I'm just going to copy it. I'm going to go like that, and do this again. All right. So this equation right here is the sum of infinitely many rectangles within a certain like lower bound and upper bound restriction. And the lower bound and upper bound restriction, this a to b right here, is hidden in this equation. That's why you don't see it anywhere. It's kind of built into the equation. It's built. That a to b, those a to b values are built into that equation up there. Okay. And what this is right here is this is a height. That's the height of a rectangle. This is the width of a rectangle. All right, so if you have a width and you have a height and you multiply them together, you have yourself an area. You have area. Right? So that's what's going on right here, is you're multiplying height and width, so you're getting the area of a rectangle. And then this sigma right here means you're adding up a bunch of area rectangles. And then n equals infinity means that you have infinitely many rectangles, which means you're going to get very close to the area of the curve, the area under the curve. So I'm going to go ahead and just draw some rectangles right here. And if you notice, I am drawing them, like I could draw them a couple of ways. I could draw them like this. See if I go like this. So you got to touch the curve at one point. So I could touch the curve there, like that, there and there. So if this is the rectangle, I'm touching the curve on the left side of the rectangle. Or, we're same with this one over here, right? On the left side of this rectangle, touching the curve. Another way to do it would be to go like this, touch the curve on the right side of the rectangle. So here's my rectangle, and it intersects the curve on the right. Here's the next rectangle, intersects the curve on the right. So we're going to do these right ones. Okay, so you could also do them from the midpoints as well, but we're going to do the right ones. So let me move this A a little bit, put it over here. All right, so this width, we're going to have these equal width rectangles. And that width is represented by delta x. Delta x. And delta x, I'll put it over here, is equal to b minus a over n. All right, so the width of the rectangle is dependent on your high boundary minus your low boundary divided by n, which is n equals number of intervals. Basically, number of rectangles. Number of intervals. Or rectangles. But in this problem, we're going to have infinitely many rectangles. Right here. Okay. But let's pretend like we don't. Let's pretend like we have 4 rectangles. All right, so let me just erase this. All right, so let's pretend like we have 4 rectangles. So I'm going to go like that, like that, like that, and like that. So here are my 4 rectangles. Okay, so, and let's pretend like this low number here is 1, and let's pretend like our b value is 4. Or actually, let's make it 3. All right, so if we use this equation for my example, then our b value is 3 minus our a value is 1 over, well, 1, 2, 3, 4 rectangles. 4. That becomes 2 over 4, which becomes 1/2. That means that if this x value is 1, then the next x value over here is 1 plus our delta x, which is the width of the rectangle, which is 1/2. So that's 1.5 or 1.5. Then you want to find out this x value over here. That's 1.5 plus 1/2, which is 2. And then you want this one over here, 2.5, and then 3. Okay, and then these guys right here, in this example, this x value right here, is that right? No, actually, since I'm doing the right side rectangle, this x value right here would be known as x1. This x value right here would be known as x2. This guy right here would be x3. And that guy right there would be x4. And they're collectively represented by the notation x sub I. So I could be any integer, and this is like the generic way of, so this x sub I right here, or I'll make it green, is the generic way of representing all of these right side rectangles. Right side x values that have corresponding, if you go here, right, they have corresponding y values, right? So this right here would be f of x1, right? And over here would be f of x2, and so on, right? So right here, that's why we talked about this being kind of like a smart input value right here, right? So those xi's, those are going to be all those right side rectangles, all right? And Delta x, well, that's the width. Okay, so let me, hold on one second. Actually, no, I'm just going to minimize all this. I'm just going to minimize this. Yeah. Kind of just put this over here. Little thought bubble. All right. So, which means nothing to do with this problem. All right, so how do we get our xi? So xi, if you look over here, the first one, or x1, right? It's a, this guy right here would be a, because there's your a. It'd be a plus delta x. All right, this location here, that x value would be a plus delta x plus delta x, right? So the first one would be a plus delta x. The second one, so I'll say x1 would be a plus delta x, and then x2 would be a plus delta x plus another delta x to scoot over to this location. X sub 3 would be a plus delta x plus delta x plus delta x, right? So a plus delta x gets you there, add another delta x gets you there, add another delta x gets you there. All right, well, we could just rewrite this. There's a cooler way to write the second one. The second one, I could write it as a plus, oops, do it over here, equals a plus 2 delta x. And there's a cooler way of writing this one over here, down below. I can write it as a plus 3 delta x. Well, notice how that number matches that number, and that number matches that number, and how that invisible one right there matches that number. Okay, so then you could write your xi as your generic way of just saying all of this is xi is equal to a plus delta xi. So that's the generic way of saying the right side of the rectangle. So generic way of saying right sides of adjacent rectangles. Right sides of adjacent rectangles along the x-axis. All right, well, all right, so back to our original problem. So we know that our original problem has a function. There is this function here, and there's this delta x, right? And we know our delta x because it's the thing times the function, and this looks awfully like a function right here. You see, so that means that this right here is our delta x. All right, so let me copy that down. All right, so that means that this right here, so it's kind of flipped, right? Because here's like the function, but here's the function, and then here's the delta x, and then here's the delta x. So right here, this part right here, or I'll just color code them. We'll just say that this right here is this part right here. Okay. And you're going to also find you're going to find a delta x inside your function. And in this case, we can easily see it. Pi for n. Okay. So let's see if we can write this a different way. Let's see if we can write this as f of xi. So how can we write this as tangent of xi? Like that. We can, because that we can write that based on this right here. Right? So tangent of a plus delta xi. And all of this together is our xi. Okay, so this I right here, it's not a sub I. This is on the same level as the x. Don't confuse it with the sub I that's right there. Okay, so this is times I, not sub I. Okay, so, all right. So how do we make this, like what do we need to put in here to make it look just like this? All right, so we could have a tangent of 0 plus delta xi. And I put a 0 there because there isn't like a 1 plus in here. All right, it's really just a delta x. It's really just this part that's in there. All right, so that means that we have tangent of 0 plus our delta x, which is our pi over 4n. All right, there's your delta x. There's your I. Great. So that means that we have our input value. I mean, we found an input value that works. We have an input value, like if we drop this, if we drop a plus delta xi into our function, as long as a is 0, we're going to get this. Well, that means that if this is a plus delta xi, our 0 must be a. A must be 0. Great. So that means that our a value, right? So our lower boundary, or our domain of where we're taking our area, starts from a. Okay. We also have our equation. We found an input that works perfectly. That means that we have a function, f of x equals tangent of x. That's our basic equation. And if we drop in xi, okay, which is this business right there, then we end up with this. And yeah, which takes us to this. Okay. So we have our function. All we need now is our boundary. But we know our lower boundary. It's 0. There it is. So we know that x has to go from 0 to something. All right. Well, let's go to our delta x. We know that delta x from up here from right here is b minus a over n. All right, so delta x equals b minus a over n. And we know what delta x is. Delta x is what's highlighted right here, because that's what's multiplied by your function right there, because that's your width. Your width is delta x, which is this guy right here, which is that guy right there. So delta x is pi over 4n. All right, so pi over 4n equals b minus a over n. But we know a is 0. So then we have pi over 4n equals b, which is what we're looking for, minus a, which is 0 right there, over n. Great. Now let's go ahead and multiply both sides by, we could say by 4n over 1, 4n. All right. And these guys completely wipe out right there, and the n's wipe out right there. And we're left with pi equals b minus 0. All right, let's get b by itself. So plus 0, that didn't do anything. And then you know that b equals pi. So now we have our upper bound. So that's what goes right there. So we know that we're going to go from 0 to pi. Or you can write it in interval notation. I'll just do it like this. So the boundary is from 0 to pi, including 0 and pi. And that's the answer. But that's not the answer, because you might be wondering what happened to the 4 that was right here. And we need to put that back into our problem. So you can, let's erase this part right here. Right there. All right, wait. So we have pi equals b minus 0. Is that b minus 0 right there? So that's just b. Times, well, the only thing that wiped out right here was the 4, was the n, not the 4. So you have to have your 4 right there. Okay. Now you have pi equals 4b divided by 4 divided by 4. B equals pi over 4. Okay. Then over here, your upper bound is pi over 4. And over here, in interval notation, is pi over 4. Now we have our answer.